Welcome back. In today's discussion, I am going to talk about Legendre transformation and Hamiltonian system of equations. Okay, so what we found in the previous discussion that whenever we have to extremize some kind of functional, okay, and we have defined functional phi, and that functional phi we have defined like this: t0 to t, and t0 to tf, and l is basically function of t, x, and x dot and dt. Okay, and we have some boundary condition. So first set of boundary condition, what we have assumed that t0 and xt0, and here tf and xtf both are known. First we have assumed that, and after that we are trying to find x star such that will extremize this particular functional. Okay, and what we found that in this particular process some equation that is called Lagrangian equation that comes into picture, and if you see, if you carefully see the Lagrangian equation, so I am writing Lagrangian equation dou L by dou x minus d by dt dou L by dou x dot equal to 0. So if you solve this equation, then I have, if x just belongs to R, then I have second order equation, and this equation may be nonlinear time varying differential equation. Okay, and sometimes solution of this equation is very complicated. Most of time I have to say that. Okay, and the generalization of this, suppose now x, if I will take x, I will define as a x1, x2 up to xn, and if that particular functional, that is function of this all state variable, at that time corresponding to each variable I have to solve one Euler-Lagrange equation. Okay, and in this way, if you will see, then I have to solve n number of second order nonlinear time varying differential equation. Okay, if both point are known to us, if suppose initial point t0 and xt0 is known to me and tf is known but xtf is free, then what we have observed that I have some way to take care of boundary condition that also comes into picture. Okay, and corresponding to that I have again solved some kind of partial differential equation. Okay, but everywhere what we found that this equation is coming, that is Euler-Lagrange equation. Okay, and this is second order differential equation. Now using this transformation, that is Legendre transformation, it is possible to show that first order set of differential equation comes into picture, and that is physically more consistent. Okay, because if you see the physical interpretation of the functional at that particular point, particularly for mechanical system, then one can tell that is nothing but energy. In the previous class we have discussed about this. So Lagrangian kind of function one can form with the help of complete energy, and after that if I solve this particular Euler-Lagrange equation after this particular transformation, that is called Legendre transformation, then we get 2n set of first order differential equation corresponding to one, because order of differential equation is not going to change. So in this particular method, means previous method, Euler-Lagrange method, I have n number of second order equation And suppose if you take very simple case, means all both end point is known to us. Okay, so if both end point is known to us, then I can tell that I have to solve n number of second order differential equation. By application of this transformation, it is possible to show that now I have to solve 2n order of first order differential equation, first order, and obviously here nonlinear differential equation is also comes into picture. Okay, so in today's lecture we are going to see the equivalence between Euler-Lagrange or Euler equation and Hamiltonian formulation. Okay, that is our main objective. But before that, I have to discuss this Legendre transformation. Okay, so let us try to see that how basically Legendre transformation works. So if you see, in order to understand this particular transformation, first what you can do, you can assume that you have some kind of function. Okay, here I am assuming that whatever y equal to fx, here x just belong to one dimensional real line. Okay, and corresponding function y, that is also real valued function, that belongs to R. Okay, and due to that reason I am able to plot this function in two dimensional plane. Here you can see that I have plotted x and here I have plotted y. Okay, another assumption I have, I am assuming that whatever this function, there that function is smooth. Smooth means I can able to differentiate at least two times. Okay, and if their second derivative is greater than 0, and during our school course we have already seen, or during our college, that if some function y equal to fx, and if their double derivative is greater than 0, then that is convex function. Okay, so what I am going to do whenever I am going to apply this kind of transformation, so I am assuming that I am just concentrating on those class of function which is convex in nature, and you are able to understand why convexity assumption is essential whenever you are going to study this transformation. Okay, so main motive is that I have to transform this particular function fx, which is initially here independent variable is x. Now I am going to transfer this function f into some new function g, and here my new variable is p. That is our main motivation. Okay, so how basically we are doing that? First we are plotting that function, and after that we are going to take some kind of number. Okay, and that number actually decide the slope of this linear line. Okay, so what I am going to do, corresponding to given number, I will select any arbitrary number p, and I am going to draw one straight line y equal to px in this same plane. You can see that this line corresponds to y equal to px. Okay, and you all, I hope that you are able to understand that why this line is passing through origin, because here y equal to px, there is no shift, so that is going to pass from 0 to 0 0 0. Okay, now how basically we are deciding p, because I am going to transform this whole function f into some function g, and where new variable is p, so I have to establish some kind of correlation between p and x. Okay, so basically how we are selecting p, we are selecting x equal to xp at which the curve is farthest from the straight line. Okay, so we are going to see that this particular line I have plotted. Okay, you can plot any line, that doesn't matter, and after that we try to see that if I drop some point from here to here, then I am going to show to see that where this curve farthest point comes into picture. Okay, so basically we are defining fpx and fpx is nothing but new function gp. And how basically we are deciding fpx? We are deciding fpx px minus fx. Okay, and we are selecting this distance that is farthest. Okay, so this point should be farthest from the curve. In that way we are defining. Okay, so if you see mathematical expression, then clearly you are able to understand. Here you can see that first I have drawn one line, linear line, so equation is px, and after that I have to check the distance between these two things. So I am going to check the distance between, suppose if somewhere I have some curve fx. So basically what I am telling now, that I have to select this px, and after that this curve, and due to that reason I have written here, you can see that here that is fp. And what I am going to do, I have to take argument of this where maximum occur. What does it mean? That I have to select farthest distance from the straight line in vertical direction. That is the meaning. Okay, so that is the interpretation of this particular operator. So argmax, argmin people are frequently using. Okay, so we are going to select those point xp, means x is function of p, where distance between px and this curve is maximum. That is the meaning. Okay, now you can see that I can also able to rewrite this, that xp in place of xp, if I will remove this, then I can tell that whatever this function comes into picture, that function is nothing but that function is gp. We have defined as a gp because our ultimate aim to convert this function f to some function g and variable x to variable p. So we have understood mathematically that what is meaning or what is correlation between this variable p and existing variable x. Okay, so I have defined gp like this. Here you can see that I am not searching argument. Here I am searching that at what point, what is farthest point, and due to that reason somehow I am going to locate the x-axis. So whenever you are going to locate x-axis, at that time I need argmax operator, and corresponding to that I have some point gp. Okay, and gp I am going to define like this, pxp minus fxp. Okay, so more symmetrical way one can also able to write like this, gp plus fx equal to px. We will see that why people are actually try to write in this way. It is possible to show that one can correlate this with Young's inequality. Several times we are going to use Young's inequality in control system or several places. Okay, so in this way what basically we are going to search now, we have to just solve this equation. And now it is possible to show that when f is differentiable, then maximization condition, that xp equal to arg max px minus fp, implies that derivative of this with respect to 2x must be 0 at this particular point. Okay, because we are going to select the farthest point and convexity condition is here, so it is possible to show that farthest point is going to lie where their differentiability of curve, this curve is going to vanish. Okay, and due to that reason basically I have this kind of condition comes into picture. So if you take the differentiation of this px, and I am taking differentiation with respect to x, and due to that reason p will come into picture and f dash equal to 0. So this kind of things comes into picture, and using by solving this equation I can able to get the p value of p. Okay, so let us try to see the geometrical interpretation. Geometrically, the tangent line to the graph of f at xp must have the slope p. Okay, so whenever we are applying this Legendre transformation, at that time what basically we are doing, I have convex function, I will draw slope of any any value. Okay, p I can select any arbitrary value. Okay, after that I have to make sure that whatever this straight line, so corresponding to that this line should be parallel. Okay, and whenever this line will touch, since these two line is parallel, it is possible to show that that is given by the rate of change of this function with respect to x at that point equal to 0. Okay, so in this way I am going to identify the point. Okay, so this is the geometrical interpretation. Now let us try to see that using some example, that how basically we are converting one function into another function using the Legendre transformation. Suppose I have some function like this, fx equal to x square. Now if you plot fx equal to x square, you can see that this is some kind of convex function. Okay, it means that my method is going to work for this particular system or particular type of function. Okay, now what I have to do, I have to draw one line. So I am going to draw one line and I have fixed px, and after that what I am going to do now, I am going to subtract px minus x square. And how basically one can define p, just I have to make sure that px minus x square and derivative with respect to this should be 0. Okay, if you keep this equal to 0, then it is possible to show that in this particular expression p minus 2x that equal to 0, because I am going to take the derivative with respect to x. And now you can see here that x is nothing but p by 2. In this way I can express relation between x and p. And now what I am going to do, I am going to substitute this x here. So if you substitute this x here, then p by 2 square become p square by 4. Okay, so in this way what happens, initially my function fx and independent variable is x. Now what happens, that again I have convex kind of function and independent variable is p. So in this way I can able to transform this to this. Okay, so I think that process is very easy. Suppose again just you have to make sure that your function, whatever function you have selected, that is convex. Otherwise it is possible to show that this condition sometime will not satisfy. If this condition will not satisfy, then you are not able to find p. Okay, so this transformation will work provided function is convex and this condition will satisfy. Okay, now suppose I have this kind of function x power alpha. It is possible to show that, now please do by yourself, that again you can write px minus x square, so x power alpha into alpha, and after that again you can calculate the derivative with respect to x. And then it is possible to show that after Legendre transformation, gp can be given by p by beta where alpha and beta is related like this. Okay, so please do this kind of calculation by yourself. Okay, suppose if you take fx equal to mx square, then this kind of things comes into picture. So please try to know, please try to do by yourself. So this is the story of the Legendre transformation. Okay, now let us try to see the some more example. So here you can see that if you have some kind of function like this is also convex function. Okay, now whenever I have this kind of convex function, so from this chord 2 to 3 I have some kind of slope p1. This chord I have slope like p0. Okay, and at that time if you again apply some kind of Legendre transformation, it is possible to show that this kind of curve comes into picture. It means that if something is convex polygon, okay, then vertex of the polygon that is converted into edge. So that kind of geometrically you are able to understand easily why this kind of conversion occur. Okay, and same kind of conversion is depicted in the figure. So just this is just for the geometrical interpretation. Now you can see that Legendre transformation is basically dual to the Young's inequality. Okay, and several places in control theory we are basically using this kind of inequality. Okay, so what is the correlation between these two? So suppose I have some function, again x is independent variable and fx, or you can write xy, so both are equally fine, where y equal to fx. After that, if I apply Legendre transformation, then that is converted into GP. So either you can write like this, or you can write fxp, because function of both p and fxp, you can write like this, that is also equally fine. It is possible to show that px is less than equal to fx minus gp. Okay, and that is coming from the geometrical interpretation, because we are going to select p in such a way such that whatever curve I have some kind of curve, and I have selected this should be farthest distance. Okay, due to that reason px should be less than equal to fx minus gp. Okay, so I am going to select some maximum. So for all x it is possible to show that this kind of inequality will satisfy. Okay, and if you apply this kind of inequality, now you can see that here what kind of things happens, that I have fx and fx x square by 2, and just now what we have seen in the previous slide, that if I have some kind of function like x square, at that time their Legendre transformation is p square by 4. Similarly, if you take x square by 2, then Legendre transformation, it is possible to show that is p square by 2. Okay, so from here you can see that directly you can able to write this inequality. You have, if you have px that is less than x square plus p square. Okay, and you can also able to confirm this kind of things. Suppose that if you have s minus p square, so I can able to write x square plus p square minus 2xp. Okay, and this is always positive, so I can write that this is always greater than 0, and if you just rearrange this, then you can see that this kind of inequality comes into picture. Okay, so either in this way or just using the help of the Young's inequality also. Now it means that if I have two functions, then always I can able to find two functions f and g. Okay, suppose I have two independent variable p and s x, so corresponding to p I can able to select some convex function, and I will get another convex function, and these two are related by the Legendre transformation. Okay, and whenever we have to solve some kind of inequality in control system, several times we are using this kind of inequality, so that is also beneficial in that particular point of view. You can see that you can also able to write px equal to x power alpha by alpha plus p power beta by beta, where alpha and beta greater than 1, and that will satisfy this kind of relation. Why? Because if you start with fx equal to x power alpha, here any convex function you can select, and there Legendre transformation you have to select, then this inequality will fulfill, and due to that reason this inequality it automatically comes into picture. So several places in nonlinear control, linear control, we are using this kind of inequality whenever we have some kind of uncertainty, disturbance, and we are going to use Lyapunov analysis. Okay, so Legendre transformation is going to help us in two different way. One way, I can able to convert one convex function into another convex function. Okay. Second thing, I am also able to get some kind of Young's inequality kind of result, because that is dual of the Young's inequality from their geometrical meaning. Okay. Now suppose if you have multi-valued function, convex function, obviously convexity is very important. Now whenever you have to check convexity, at that time you have to calculate second derivative, means you have to calculate Jacobian matrix, and you have to make sure that is positive definite. Then only I can tell that whatever fx, and here x is nothing but x1 up to xn. Okay, either you can take as a column vector or row vector, that doesn't matter. And after that, if you select second derivative, the result is exactly the same. So suppose I have some convex function, and if I will take second derivative, and then if that is greater than 0, then we are telling that it is convex. Here, instead of that, now this is multivariable case. So due to that reason, now what you have to do, you have to form the quadratic form of these two, and after that we have to check that matrix, whatever matrix, Jacobian matrix that comes into picture, that should be positively definite. Then only I can confirm that this multivariable function fx is convex. Again, I can define everything exactly in the same way, and after that I have to solve p I can get using the solution of Jacobian. And here you can see that p, now that is not single valued. Corresponding to x1 I have p1, corresponding to x2 I have p2, corresponding to xn I have pn. Okay, so this is just generalization of the scalar case, whatever we have discussed so far. Okay, so up to here anyone has confusion? Then please let me know. So main idea is, I have some kind of convex function. Using Legendre transformation, what I am going to do, I am going to convert into another convex function. Okay, and we are going to understand that what is benefit of this transformation using the help of Lagrangian system. Lagrangian system means I have some kind of functional, I know the end point might be fixed, might be changing. Okay, and after that I have, if I solve the extremization, at that time Euler equation comes into picture. Okay, and that system of equation is called Lagrangian equation. Okay, now what I am going to do, I am going to apply transformation, whatever we have learned so far, that is Legendre transformation, to that particular Lagrangian system. Okay, and it is possible to show that I will come up with 2n first order equation, and that is called Hamiltonian system of equation. Okay, so let us come to the derivation of that. Now first I will write the theorem, and after that I will come to the mathematical proof of this theorem. Okay, so what I am going to do, since I know that I have to extremize this function, and when I have started this lecture, at that time I have written that function t, x and x dot dt. At that time, if I know the end point, I am assuming very simple case. At that time, what we found, that I have to solve this equation, dou L by dou x minus d by dt into dou L by dou x dot equal to 0. Okay, now what we are going to do, I am going to define this function dou L by dou x. In place of x, I have selected another variable, that is q. Okay, so either you can write this function like this, L, T, X, Q and Q dot. So jo physical interpretation is not going to change, just variable is going to change, but physical interpretation of everything remains the same. Okay, now what I am going to do, I am going to assume this quantity, this dou L by dou x or dou L by dou q by p dot. Okay, so or you can think like this, if I define this quantity as a p, dou L by dou x dot equal to p, then dp by dt is nothing but dp by dt, and this equal to 0. Due to that reason, p dot is dou L by dou x. Okay, so what I have done, first either you can think like this, q dot or dou L by dou x dot, both are same for me, that I have defined like p. Okay, now this, after definition of this should satisfy this equation, Euler-Lagrange equation, if this particular trajectory x star or q star is going to extremize this function. So obviously this Lagrangian formulation should be satisfied, Euler-Lagrange formulation should be satisfied. It means that dou L by dou x equal to d by dt dou L by dou x dot. Okay, and due to that reason, P dot equal to dou L by dou X and or Q. So this kind of things basically comes into picture. Here I am assuming that I have assumed in reverse order, but time is here. Due to that reason, this kind of formulation is written. It means that L is nothing but Q dot. So you can able to write in any order, that doesn't matter. Okay, so real number, this is n dimensional and this is n dimensional, and since I have to extremize that functional, due to that reason whatever this quantity, that should be a scalar, and due to that reason I have written this kind of mapping. Okay, it is possible to show that directly I can able to get these two equation, these two first order of the partial differential equation, that P dot is new variable, and after that Q dot, that is dou H by dou P. Okay, in this way, and here H is nothing but PQ dot minus L Q dot T. Okay, so try to think this whole things like this. I have initially some kind of function, that is Q dot T. Okay, after that what I am going to do, I am going to apply the Legendre transformation such that that is going to convert into some other variable, that is h. Okay, so for that what we have seen, that I have to write px, and after that whole function fx we are writing like that. So similar kind of terminology here we are using. P I have chosen in place of x since q is here, and it is possible to show that I am going to select Q dot only here. Okay, so some kind of matching people has thought. Okay, using proof you are able to see. So Q dot, if I will select in place of X, then what happens here, PQ dot comes into picture and this function remains as it is. In this way I can able to define another variable. Okay, and this transformation is nothing but the Legendre transformation. Okay, and that involve Q dot, because here whatever variable is here, I am assuming that whatever I have functional, that is function of Q dot, I am not tempering Q remains as it is. Now I am going to convert this into something, some another variable, extra variable I am going to introduce, and there in that particular extra variable I am going to define some kind of new convex function. Okay, so let us try to come to the proof. So proof is like this. I am assuming that because I have to apply Legendre transformation, so first assumption, since I am going to take this variable q dot, so I have to make sure that whatever this functional, that should be convex with respect to q dot. That kind of things means, it means that whenever I am going to formulate the sum, because whenever you are going to solve the optimization problem, at that time this function people are selecting based on their requirement. Okay, so I am going to do those kind of selection where this function L is convex with respect to rate of change of some variable. So suppose here q variable, then q dot, so that should be convex with respect to q dot. Okay, and convexity, in order to check the convexity with respect to q dot, I have to take the second partial derivative, and again some quadratic form comes into picture, and I have to make sure that is positive definite. Okay, now I have already seen that if I am going to do transformation in terms of q dot, then I can able to write expression like this. I am just bothering about the q dot, so I have written like this, and I know that I have defined p equal to p. I know that I have defined like d pi by dl by dou L by dou q dot. Okay, so if you take the differential of h, so h basically contain term, here I have written q dot, but basically this L is not function of q dot and t, and due to that reason dou h by dou p and variation with respect to p comes into picture, dou h by dou q variation with respect to q comes into picture, dou h by dou t and variation with respect to t, that comes into picture. Okay, and from here we know that whenever I have this kind of function, then total differential of pq minus l for p equal to dou l by dou q dot. Okay, so how basically we are doing that? I have told you that whenever I have px minus some fx kind of things is there, at that time in order to calculate the p, I am taking the partial derivative of this whole things with respect to x. Okay, so similarly here I have to take the partial derivative of whole things with respect to q dot, because we are assuming this just q dot, and due to that reason p minus dou l by dou q dot equal to 0, and due to that reason this is the motivation to define p equal to dou l by dou q dot, whatever we have seen in this particular theorem, because we have chosen p equal to dou l by dou q dot, and once I have chosen, then dou l by dou x or dou q is become p dot, that is automatic. Okay, so now since first I have calculated variation in dh for original function, and after that I have again calculated the variation whenever I have expressed like this. So at that time it is possible to know so that these two variation are equal, and if you just equate it, it is possible to show that I will end up to the same equation whatever I have written. Okay, whatever I have written like this and this. Okay, so just by equality you are able to land up to that particular conclusion. Okay, so in this way and reverse way, what you can do, that it is possible to show that p dot and q dot will satisfy the Hamiltonian equation. Okay, so basically here we are talking about equivalence, and whenever we are talking about equivalence, it means that if you assume Lagrangian equation, then this condition will satisfy. If this condition comes into picture, then Lagrangian equation should satisfy. So if you just substitute this condition inside the Lagrangian equation, then automatically that will satisfy. Okay, so in this way, finally what we are telling, that if I will formulate h function, okay, and if I, and how basically one can formulate, if this functional is given, so I will select q dot and I will write this kind of transformation. So this is coming from the Legendre transformation, but I am going, since this first time this is applied by Hamiltonian, so this function is now known as a Hamiltonian also. Okay, so I am going to formulate Hamiltonian function with respect to q dot. Okay, and after that it is possible to show that p dot and q dot second order equation is just converted into first order equation just by this kind of formulation. Okay, now let us, this is the proof. So I have already discussed the proof. Now try to see this kind of correlation for the mechanical system. Okay, so what we have observed in case of mechanical system, that whenever we are defining the Lagrangian, so at that time whenever I am defining Lagrangian, at that time we are defining Lagrangian equal to kinetic energy minus potential energy. Okay, and kinetic energy is actually comes into picture for mechanical system by the virtue of the rate of change of something, and due to that reason I am assuming q is my state variable. So rate of change of a state variable is responsible for the kinetic energy, or all set of since energy is going to lie with respect to each and every state, and due to that reason I am going to select all kind of combination where aij is nothing but some kind of function which is function of q and t. Okay, and after that now I have u is potential energy, that is just due to the virtue of the position or a state vector. Due to that reason I am assuming that u is function of q, but this t is function of q dot. Okay, here in some case aij is constant. Okay, in some case it is also depending on q. Okay, so that is depending on the situation. So suppose that if I have single mass, then at that time we are defining half mv square. Okay, but if mass is also varying, okay, that do not remains constant, at that time it is possible to show that second representation, that is function of time and function of a state, that also comes into picture. Okay, So this is the generalized formulation of the kinetic energy. This is the generalized formulation of the potential energy. Okay, it is possible to show by using that kind of transformation that whenever we are converting Lagrangian into Hamiltonian in this particular process, initially Lagrangian is defined as a kinetic energy minus potential energy. Now after this transformation, that Legendre transformation, what happens that now H is given by kinetic energy plus potential energy. It means that that is converted into total energy. Okay, so I have complete physical interpretation now. What we are going to do now, we are going to see the total energy, and we know that if I know the energy H, then I can able to formulate differential equation. How we will get the differential equation or evolution equation, that P dot equal to minus dou H by dou Q. It means that if I know the total energy, then directly I can write these two equations, and that equation will characterize the motion of the system. So particularly for mechanical system, I have clear cut interpretation of physical means kinetic energy and potential energy. So I will calculate kinetic energy, potential energy, and after that I am going to add it, and I am going to substitute in that particular Hamiltonian formulation, and that will give us the state space representation of some mechanical system. Okay, or dynamical equation of the some mechanical system. Okay, so let us try to see the equivalence. So what equivalence is telling, that it is possible to show that where we are going to perform the this transformation at that point fx equal to gp. We have seen that in the example, because this is tangent here, so this point here, this point, because we are talking about some new function gp, so at this particular point both things are coincide, and due to that reason fx equal to gp. From plot also you are able to see. Okay, now it is possible to show that f is homogeneous function. So if I have some kind of homogeneous function, and if I take partial derivative, and after that if I multiply with same, then I will get 2f. Try to see like this. Suppose you have some function fx equal to x square. Okay, and if you take the derivative of this f dash x, then you have 2x, and if you multiply this with x again, f dash x into x, then you can see that 2x square, and 2x square is nothing but same function. So due to that reason 2f. So this kind of result is valid, even if you have now, you can take x cube and try to check that same kind of formulation that comes into picture. Okay, so this is true for any homogeneous function. Okay, that result I am going to use, and gpx, new function after Legendre transformation, that is px minus fx, and p I know, because how basically we are calculating p here, p equal to dou fx by dou x. So in place of p, now I am going to substitute dou f by dou x, and I know that dou f by dou x is nothing but 2f, so 2f minus f is basically fx. Okay, so in this way I can able to show that gp equal to fx. Okay, whatever this theorem is suggesting, whatever this lemma, because this result I am going to use to the further proof. Okay, now what I am going to do, suppose I have this kind of function fx equal to x square. Okay, and we know the property of tangent to the parabola, that fx equal to half mx, and p I can able to select mx, then gp is nothing but p square by 2m. We have already seen by Legendre transformation. Now I know that h equal to pq dot minus l. Okay, now if you see carefully that interpretation of p and q, so p is dou f by dou x, and q is nothing but, so basically this whole term is nothing but dou f by dou x into x. So same function 2f that comes into picture, and here f is nothing but the kinetic energy, and due to that reason 2 of kinetic energy comes into picture. Lagrangian we know for mechanical system, that is kinetic energy minus potential energy, and due to that reason this become kinetic energy plus potential energy. Anyone has confusion? Then please let me know. If anyone has confusion on this particular formulation, then please let me know. Okay, if you don't have confusion, it means that this theorem is true. Okay, it means that Hamiltonian is nothing but the addition of kinetic energy plus potential energy, and Lagrangian we have already seen. Okay, that is kinetic energy minus potential energy. Okay, so in this way, now this lecture is in from my side. Now I am going to conclude this lecture. What basically we have seen, that I have some kind of functional. Okay, and I have to extremize that functional. I know the boundary point. Then Euler-Lagrange formulation comes into picture. Euler-Lagrange equation is second order non-linear non-autonomous differential equation. Okay, we have also seen the beauty of state space representation, and whenever we are formulating a state space representation, at that time we are getting some kind of condition using first order differential equation, or dynamical evolution of system I can characterize using first order differential equation. Okay, it is possible to show that whatever Euler-Lagrange equation, after this kind of transformation, that is called Legendre transformation, that is converted into first order differential equation. Okay, two set of first order differential equation, and mechanically if we see, then they have clear cut physical interpretation, that they are talking that system will evolve in such a way such that total energy of the system somehow that is extremized. That is the interpretation of the Hamiltonian formulation. Okay, and in order to get Hamiltonian formulation from the Lagrangian, we are going to use the Legendre transformation, and Legendre transformation is also help us to establish Young's inequality, that is dual of that. So one can get benefit of Legendre transformation in two different way. One way to formulate Young's inequality, second way to convert Lagrangian formulation into Hamiltonian formulation. Okay, so difference is, if you see mechanical point of view, then difference looks very clear, that Lagrangian, that is equal to kinetic energy minus potential energy, Hamiltonian, that is total energy. Okay, so whenever we are trying to get the evolution of the system, okay, and we know that almost all system in nature that is evolve in optimal way, and due to that reason they are going to satisfy some kind of optimality principle. Okay, so they are optimizing themselves, and due to that reason now I can able to express the evolution of that system using these two first order differential equation. Okay, so now lecture is concluded from my side. If you have any confusion, then please let me know. Okay, so what kind of exercise now you have to do? You can take any mechanical system, any electrical system, formulate the kinetic energy, potential energy. Okay, after that you can take the summation of that, and two equations P dot whatever I have told, that H you can formulate, that is kinetic energy plus potential energy, and after that P dot equal to minus dou H by dou Q, or dou Q dot you can take, that will give you first equation. Similarly you can get the second equation. Okay, so this will also help you to do mathematical modeling of some particular physical system, particularly mechanical, electrical, or equivalent. In last class I have already told you, talk about that how to, if I have electrical system, so how to establish what is corresponding kinetic energy concept for the electrical system. So that kind of equivalence we have to use. So lecture is now in from my side. If you have any confusion, then please let me know. Anyone? Okay, please again go through that. If you have any confusion, then please let me know. So thank you very much.